Hello friends, welcome back to Synapsara. In the previous video, we explored gradient descent, the workhorse of optimization in machine learning. But today, we're going to look at something even more powerful, conjugate gradient descent, or CGD for short. If gradient descent is like hiking down a mountain in a straight line toward the steepest descent, conjugate gradient descent is like having a GPS that finds the smartest path down. Let's dive in. So what exactly is conjugate gradient descent? CGD is an optimization algorithm that finds the minimum of a function much more efficiently than standard gradient descent. It's particularly powerful for solving large systems of linear equations, the kind you find everywhere in physics, simulations, image processing, and deep learning. The magic? It uses something called conjugate directions instead of just following the gradient blindly. Let's start with the math. Don't worry, I'll keep it intuitive. We want to minimize this quadratic function. F of x equals 1/2 x transpose ax minus b transpose x. Now, if you remember from calculus, minimizing this function is actually equivalent to solving the linear system ax equals b, where a must be symmetric and positive definite. This is crucial. The gradient of our function is simply ax minus b. Remember from my gradient descent video, the gradient points in the direction of steepest ascent. So we move in the opposite direction to descend toward the minimum. Standard gradient descent does exactly this at every step. But here's the problem. This creates a zigzag pattern, especially when the function has an elongated valley shape. It's inefficient. This is where conjugate directions come in. And this is the heart of CGD. Two directions di and dj are called A-conjugate if d I transpose ad j equals 0 when I is not equal to j. Think of it like this. In regular geometry, orthogonal vectors are perpendicular. They have a dot product of 0. Conjugate directions are similar, but instead of using a regular dot product, we use this A inner product. And here's the beautiful part. If we search along conjugate directions, each step is completely independent from previous steps. We don't interfere with the progress we've already made. In fact, for an n-dimensional quadratic problem, CGD is guaranteed to find the exact solution in at most n steps. Compare that to gradient descent, which could take hundreds or thousands of iterations. Alright, let's see how the algorithm actually works. I'll walk through each step, and trust me, it's more elegant than you might think. Step 1. Initialize. We start with an initial guess, x, 0. Then we compute the residual r, 0, which is b minus ax, 0. This residual is actually the negative gradient at our starting point. Our first search direction, d, 0, is simply equal to r, 0. We start by going along the gradient, just like standard gradient descent. Step 2. Compute the step size. Here's where CGD gets smart. We don't need a learning rate. Instead, we compute the optimal step size alpha using this formula. R transpose R divided by D transpose AD. This gives us the exact step size that minimizes the function along the current search direction. No hyperparameter tuning needed. Steps 3 and 4. Update position and residual. We update our position, x k plus 1 equals x k plus alpha k times d k. Then we update the residual, r k plus 1 equals r k minus alpha k times a d k. Notice we're updating the residual without recomputing ax from scratch. This is much more efficient, especially for large matrices. Steps 5 and 6. This is the magic. We compute beta. Beta equals r, k plus 1 transpose r, k plus 1 divided by r, k transpose r, k. Then we update the search direction. D, k plus 1 equals r, k plus 1 plus beta, k times d, k. This is not just the gradient. We're combining the new gradient with the previous search direction weighted by beta. This creates a conjugate direction that's guaranteed not to undo the progress we've made. Step 7. Repeat until convergence. We keep iterating until the residual is small enough. And here's the key insight one more time. CGD uses conjugate directions instead of just the gradient. This prevents zigzagging and converges much faster. For a 2D problem, CGD converges in just 2 steps. For a 100-dimensional problem, at most 100 steps. That's incredible efficiency. Now let's see this in action. I've set up a visual comparison. Standard gradient descent on the left, conjugate gradient descent on the right. We're minimizing the same quadratic function. You can see these elliptical contours representing the function's shape. Both algorithms start from the same point in the upper right. Watch gradient descent first. See that? It's zigzagging back and forth. Step 1, perpendicular turn. Step 2, perpendicular turn again. This is the classic problem with gradient descent on ill-conditioned problems. The gradient keeps pointing perpendicular to the valley, so we bounce from side to side like a pinball. After 8 iterations, we're finally close to the minimum, but we're still not quite there. In practice, this could take dozens or even hundreds of steps. Now, watch conjugate gradient descent. Step 1, and it's already making smart progress along a diagonal path. Step 2, and we've hit the exact minimum. Just 2 steps. For this 2-dimensional problem, CGD needed exactly 2 iterations to converge perfectly. No zigzagging, no wasted motion, just intelligent optimization. Let's compare the numbers. Gradient descent, 8 plus iterations. Conjugate gradient descent, 2 iterations. That's a 4x speedup on a simple 2D problem. Imagine what this means for a 1000-dimensional optimization problem in deep learning. Now, let's talk about why CGD works so well. What are the theoretical guarantees? Let's go through the key convergence properties. Property 1, exact convergence in n steps. For an n-dimensional quadratic problem, CGD is guaranteed to find the exact solution in at most n steps. Not approximately, exactly. This is because we're searching along n mutually conjugate directions, which form a basis for the entire space. Each step solves the problem completely in that direction. Property 2, no learning rate needed. Remember how in gradient descent we had to carefully tune the learning rate? Too small and convergence is slow, too large and we overshoot. With CGD, the step size is computed optimally at each iteration using that formula we saw earlier. One less hyperparameter to worry about. Property 3, A-orthogonal directions. The conjugate directions are A-orthogonal, meaning each step is independent from the others. When we take a step along direction dk, we don't disturb the minimization we already achieved in directions d, 1 through d, k1. This is why we don't zigzag. Each step makes permanent progress. Property 4, memory efficient. Despite its power, CGD only needs to store a few vectors in memory: the current position, the residual, and the search direction. We don't need to store the full history. This makes it practical even for huge problems with millions of variables. And here's the theoretical guarantee. For a quadratic function with condition number kappa, which measures how elongated those elliptical contours are, CGD converges in O of square root kappa iterations, while standard gradient descent requires O of kappa iterations. If kappa is 100, gradient descent needs about 100 iterations, but CGD only needs about 10. The speedup grows with problem difficulty. So where do we actually use conjugate gradient descent in the real world? It turns out everywhere. 1. Computational physics and engineering, solving large, sparse, linear systems. Think structural analysis of bridges, heat distribution in materials, electromagnetic field simulations. 2. Medical imaging, image reconstruction in CT scans and MRIs. When you get a medical scan, CGD is often working behind the scenes to turn raw sensor data into clear images. 3. Deep learning, training neural networks. While most modern deep learning uses variants of SGD with momentum, CGD-inspired methods like nonlinear conjugate gradient are used for certain optimization problems. 4. Finite element methods, structural analysis in mechanical engineering, predicting how buildings, cars, and aircraft will respond to forces. 5. Computational fluid dynamics, simulating airflow over airplane wings, water flow through pipes, weather patterns. CGD helps solve the massive systems of equations that govern fluid motion. The common theme? Large-scale optimization problems where efficiency matters. Let's wrap up with the key takeaways. CGD is much faster than standard gradient descent, often by orders of magnitude. Guaranteed convergence in n steps for n-dimensional quadratic problems, that's exact, not approximate. Uses conjugate directions to avoid zigzagging. Each step makes permanent independent progress. No learning rate tuning required. The optimal step size is computed automatically. Ideal for large-scale optimization, memory efficient and fast, perfect for problems with millions of variables. Here's the bottom line. Conjugate gradient descent. Smart optimization through conjugate directions. It's elegant math that leads to practical speed. And that's beautiful. Now, I know what you're thinking. That's great for quadratic functions. But what about real-world nonlinear problems? Great question. Let me show you something really cool. I've implemented both gradient descent and conjugate gradient descent on the Rosenbrock function by NE, also known as the banana function, one of the most challenging test functions in optimization. It has a narrow, curved valley that makes optimization really difficult. Let's see how both algorithms handle it. Here's what we're dealing with. The Rosenbrock function in 3D, see that long, narrow, curved valley? This is what makes optimization so challenging. First, let's watch the race animation. On the left, standard gradient descent with momentum. On the right, conjugate gradient descent. Both start at the same point. Look at gradient descent. It's taking tiny steps, bouncing around, making slow progress. Meanwhile, conjugate gradient is making much larger, smarter steps. It's adapting its search direction to follow the valley. And CGD converges in 876 iterations, while gradient descent takes 3,155 iterations. That's a 3.6x speedup. Now, let's see all 4 starting points converging simultaneously. Watch how all the paths eventually find their way to the global minimum at 1, 1. Some start far from the valley, others start right in it. What's impressive is that conjugate gradient consistently converges faster from every starting point. The speedup ranges from 2.8x to 3.6x depending on where we start. This isn't cherry picking. CGD is consistently superior. The convergence dashboard tells the full story. Top left, objective function value over iterations. See how CGD solid lines drops much faster than GD dashed lines? Top right, distance to the optimum. CGD makes steady progress, while GD plateaus multiple times. Bottom left, iterations needed. The green bars, CGD, are consistently shorter than the pink bars. Bottom right, speed up factors. Every single starting point shows 2-4x faster convergence. Finally, this 3D rotation shows the paths from all angles. You can see how conjugate gradient navigates the banana valley intelligently, while the surface itself reveals why this function is so challenging. This is nonlinear conjugate gradient in action, not as theoretically perfect as the quadratic case, but still dramatically better than standard gradient descent. So what have we learned today? Conjugate gradient descent is a powerful optimization algorithm that exploits the geometry of the problem through conjugate directions, converges in n steps for n-dimensional quadratic problems, requires 2-10x fewer iterations than gradient descent in practice, computes optimal step sizes automatically, scales to massive problems with millions of variables. It's used everywhere, from medical imaging to aerospace engineering to machine learning. If you want the code for the animation and simulations, then comment down. If you enjoyed this deep dive into optimization algorithms, hit that like button and subscribe for more. Next time, we'll explore even more powerful optimization techniques. Thanks for watching and happy optimizing!